Okay, so here we are, still in our nuclear bunkers, waiting for the end of the world. Let's this week deal with another one of those objections that we often get when we discuss the concept of fine-tuning. And of course, we've heard all these arguments before, and as we did in our book, A Fortunate Universe, available from all good and not so good booksellers, we discussed our reactions to a number of these objections. And so this week, one of the things people often raise is, what about other forms of life? Are you just focused on life on Earth based on carbon? What about other life based on other chemicals, or life not based on chemistry at all? What do we say?
Well, this is a lot of fun to think about. Let's just say that right out of the gate.
Absolutely.
It is a lot of fun to think about, like, especially once you realize how particular our form of life is, the particular reactions, the particular way that, the particular chemicals we use, all that sort of stuff. But in terms of the fine-tuning of the universe for life, there is a good point that is made here. We want to know, out there in other possible universes, I've changed the mass of the electron, I've changed the way the universe expands, all that sort of stuff. Could there be any form of life, not just one that looks a bit like me, but any form of life out there? So we do need to consider that. But I think the point you got to make, first of all, is in order to overturn the conclusion we have that life seems to be fine-tuned, that it's only in a very small sort of fraction, small subset of the other possible universes out there that you could have life. In order to overturn that conclusion, there'd have to be some form of life or forms of life that could just exist in any old universe out there, right? So we tried to map out the whole of here's a whole lot of possibilities, and here's us, and what happens out here. Well, we said that life couldn't exist in massive big bits of this sort of parameter space, and to overturn that, it's not enough to just come up with some other form of life. It's got to be some other form of life that could exist out here or over there or under here. So we need some form of life that's gonna hold itself together in all these other weird and wonderful universes.
So let's bring it back to our universe to start with. And I'm gonna put up a book that I've recently finished reading. So this book I recommend. Oops, it disappears into the background. It's called The Equations of Life, and essentially this book discusses the fact, asks the question about life in the universe, and points out that life in this universe, on a very different planet to our own, is still bound by the same laws of physics that we have here on Earth. So we can work out an awful lot about life, potential life out there in the universe, based upon the fact that we know the laws of physics here. And what we did, of course, in our book is ask the question about life in other universes where the laws of physics are different. But things are still bound by the laws of physics. And one of the things that we know as cosmologists is that if we look at the distribution of elements in the universe, we know that hydrogen and helium are the most common, formed in the Big Bang. Elements then heavier than that, other than the few very close to hydrogen and helium, essentially forged in stars. Mm-hmm. And the most common elements in the universe, other than hydrogen and helium, are actually carbon and oxygen.
Yeah.
And they are the elements that life on Earth has basically used. It's the building blocks for life on Earth, is because there's plenty of carbon around. We're carbon-based life forms, and we have oxygen built into our systems. But there is the question of other elements that could form the backbone of life.
Yeah. So there's an objection here, which is some, I don't know who coined this term, but it's really nice. Carbon chauvinism.
Carbon chauvinism.
We just assume that because if there's some other bit of this parameter space out here where there's no carbon, we say, well, there's no carbon and we're made of carbon, so there can't possibly be life out there. But there's a lot more to it than that. So for example, we did this in the book. You can just look along, say, the first row of the periodic table and say, all right, I've got, you can have that element and hydrogen. so for example, beryllium is on the top right. Here's beryllium, here's hydrogen. Have as much of that stuff as you want. How many different chemical compounds can you make? Include, all the different ways you could hope to stick them together, pull an electron off and make them charged, all that sort of stuff. And so as you go across the periodic table, lithium and hydrogen, you can make 4. Beryllium and hydrogen, you can make 6. You get numbers like this. So you get nitrogen, you can actually make 65. So with just nitrogen and hydrogen, you can make 65 elements. And then carbon, you can make about 29,000. And if you went across just do it with the rest of the periodic table, carbon would be miles ahead of everything else, including silicon. For silicon, it's 55.
Yeah, but we should point out the important thing about carbon and silicon is that if you look at the periodic table, they're above each other.
Yes.
Right? And the reason that they're above each other is that they have the same sort of outer electron configuration.
Yeah.
Right? You have your nucleus, you have your electrons going around, and chemistry is the physics of the outer electrons, right? It's how do things interact with other things, and it's normally via what's going on in your outermost electrons. And the structure of a carbon nucleus is distribution of electrons, the outer electrons, and silicons are very similar, so they can do similar kinds of reactions.
Yeah, so if you remember your chemistry, the elements that are in the same row of the periodic table are similar. That's about as much as I remember. The same column. Well done. Sorry, I've been teaching programming, and so columns and rows are in my mind. So it's not the case that we say if you don't have carbon, well, it's not really the case that we say if you don't have carbon, you can't have life at all anyway, in a lot of the fine-tuning sort of cases. So if we think about the cosmological constant, if you put too much of it in a universe, it expands too fast. If you put a negative amount and too much in the universe, everything collapses very quickly. The argument that there won't be life in that kind of universe is just, nothing will touch anything else, or everything will touch everything else in a giant crash in about 1 second's time. So we haven't really worried about carbon in that universe at all. But even when we focus on carbon, we didn't do that just because we're made of carbon. We have the periodic table. We can do chemistry. We can start to put things together. Carbon is by a long, long way. I mean, we're talking here a factor of 1,000 on average, more chemical compounds across that, first line of the periodic table, and even down the same column, that you can make that many more elements with this thing. So if there's another form of life out there that's not based on carbon, it's hard to know how it would make the sort of variety of compounds it would need to do sort of the energy processing, information storing things that life needs to do.
Yeah, and this gets back to this central. I think what is central to the story we have in our book. It's not necessarily life that's the defining thing here. Yeah. It's the complexity that you need for life. And again, in this book about the equations of life, they talk about the various molecular structures you need inside each cell in your body to process information, to carry energy from one place to the other, etc. And it's all complex molecular machinery.
Yeah.
You can't build that molecular machinery, which carbon allows you to do. It gives you very versatile backbones. Yeah. And you can't have the complexity that life appears to need.
Yeah. So silicon's a good case for this, actually. With silicon, what it can make long chains of compounds, but they tend to be repeating chains.
Yes.
So sand is silicon oxide, but it forms a crystal. So it's not. So it's just the same thing repeated over and over. Whereas carbon has the ability that we've not really seen in any of the other elements to actually make something like DNA, where it's not just a repeating. You can actually write a sequence. So your DNA, the reason it can store information is because it's not just a simple repeating pattern. It can, think about the words in a book. It can't just be a repeating pattern of letters. It's got to actually mean something, right?
Yeah, I think it was Schrödinger in his in his book, What is Life, that pointed out that life is unlikely to be based on crystals because crystals just
Yeah.
are too simple.
Yeah.
There's no way to encode information in there without having to do something a bit funky.
Yeah. I mean, the other point to make about silicon is, suppose, we've mapped out the whole of of the possibilities here, and okay, we found a tiny little area where here's where the carbon-based life can be. Suppose we did actually make this assumption that it has to be carbon, and you go, well, what about silicon-based life? Well, I mean, the conditions in the universe you need to make silicon are pretty similar to the ones to make carbon. You've got to have stars and supernovae to go off. And so if carbon is in a small space, silicon, it's not only going to be in a small space as well, because you need similar conditions. It's going to be a small and overlapping space. So you might get, the difference between this and then just, oh, there's the silicon bit. And so the whole fine tuning picture just doesn't change. You've just got a tiny region just gets a little bit bigger on one side. And that's kind of all there is to it.
Yeah. So I mean, I thought about this a little bit. We've spoken, and we will do a video at some point on the Hoyle resonance and the production of carbon in the universe, and point out that there are some interesting things to do with the energy levels in nuclei, which means you can create lots of carbon, but then that carbon doesn't automatically get processed all into oxygen and then into heavier elements. Yeah. So we have lots of carbon in the universe. But we could imagine a universe where that happened, and instead of there being lots of carbon, there would be lots of silicon instead. And there would be life in that. There would be the potential for complexity at some level and life in that universe. But that universe itself is not that dissimilar to our own, right? Yeah. We've only moved a little bit in parameter space. We still have stars. They still burn. They still produce heavy elements through nuclear fusion. Except we've got, instead of having lots of carbon, we've got lots of silicon. That is a universe not too far of a step away from our own.
Yeah.
Right? Not somewhere radically different in parameter space where you don't get stars at all.
Yeah. So actually, well, I was going to say, once you start thinking about the fun thing, which is all the alternative forms of like alien life that you find in fiction, once you sort of look at the other possibilities within sort of fine tuning, they all start to look a bit samey.
Yeah.
Chewbacca. If evolution on Earth had taken a slightly different part, we could have had Chewbaccas around here. We could have had Ewoks. Could have xenomorphs. They're just not. They're not that different. So it actually, the most different sort of life that gets considered in fiction is the gas cloud.
Yeah.
The life cloud. So actually, your shirt there, Fred Hoyle. What a wonderful shirt that is, bespoke, one of a kind. So that's Fred Hoyle. We should explain. So he wrote a fiction book called The Black Cloud, which I recommend. It's a good read.
He wrote a number of books.
Yeah.
Of fiction, and A for Andromeda is really good as well. So we recommend some of Fred's, not all of it. It's not all of it, but some of it, especially the Black Cloud. So during the premise,
I haven't read enough to know the I don't want to sort of ruin it, but we're sort of slightly going to give away a little bit of the ending here. But an enormous cloud of gas is heading towards the solar system, but starts to move in a way that is not just purely falling under gravity, and it turns out to be a sort of superorganism, and they nickname it Joe. And it turns out to be vastly more intelligent than human beings. And so when it finds life on Earth, it's we're surprised to find life in a cloud, and it's surprised to find life on Earth. And it's a really interesting little book about what how everyone reacts and what that would do to life on Earth. But the problem is, the way it's supposed to send, I think what Hoyle had in mind was it's a cloud, but it sort of works like a giant brain, except that it's in the gas state. And so it sends, whereas we've got, neurons sending things around, it's sending things along like magnetic field lines through space. And so one of the problems is, because it's huge, that's really hard to do. And also sort of the solid state, like, we're solids, right? You're sending a signal along a solid wire is fine because you know where the start and the end of it's going to be. Making something stable out of magnetic fields and fluids and gases is extremely difficult. They're subject to all sorts of complexities and instabilities and chaos and all that sort of stuff. So, even in the book, there's one of the scientists who in the book, who's presumably speaking for Hoyle, says, what's amazing is that even though it's very different in its makeup, the details are the same. It uses gas instead of blood. It has its own electromagnetic heart, electromagnetic kidneys to filter out the stuff it doesn't want. The logic of the layout is all the same. So if we expanded our view of life to include Joe, a sentient gas cloud, it still wouldn't change the picture of fine tuning very much. You still need different particles to do this sort of stuff, to sort of maintain the electric field or magnetic fields and to do all that sort of stuff. You still need structure to form in the universe. So
you need a sufficient level of complexity. And of course, that's without bringing the questions of how a creature like Joe could have arisen, right? I mean, that almost then gets back to one of Hoyle's arguments about complexity of life on Earth is that if you look at the structure of DNA, the chances of that occurring at random is like the chances of a 747 being assembled by a tornado tearing through a junkyard.
Yeah.
Pieces again. Of course, it's a somewhat specious argument because our structure evolved from simpler things. But how would we think that that Joe's structure evolved in a similar kind of way, right?
Yeah.
Where either Joe basically was born fully formed, or he and his kind, he, she, it, and its kind evolved. But how do we imagine that process taking place on Earth? We think that we had the warm little pool where we could bring chemicals together. What would the equivalent be on the cosmic scale? And that doesn't mean that we shouldn't think about things like that, but it's hard to imagine or hard to bring to mind the sort of conditions that could have existed for Joe to have arisen in the universe.
Yeah, so there's a big question mark hanging over all this about how life forms for us, in the first place, and so how it could form anywhere else in the first place. When we think about fine tuning, we try not to be beholden to that whole discussion. We don't want any of our conclusions dependent on that sort of thing, and so we try to just lay out the most general conditions that we need to lay out, and so we're not having to think about those sorts of things. But that's the answer to that objection. What about other forms of life? Well, they'd have to be extremely versatile. I can exist in any old universe kinds of life, and so it'd have to be very simple things. If you can exist in a universe where the cosmological constant has made everything expand away from everything else, so there's sort of 1 proton per trillion light years. If you've got a form of life that can exist in that environment, it must be a really simple form of life. And so, what is it? Just tell us, right? There's no need to just say, oh, it's possible. You should be able to just tell us what the plan is. If you can make life out of 2 protons, then tell us how are you going to do it.